of integrability, yes. So this is, first of all, thank you the organizers for well, putting up this conference and for allowing me to talk here. My hope is definitely that I can actually use all this time in at GGI to continue further this work, because there's just too many unknowns. So I'm just going to motivate all the work that we've been trying to do ever since. So this work is basically what's contained in the paper of already a year and a half ago. But well, we've tried many different things from then on. Unfortunately, just there's more unknowns than actual full understanding. So the main idea is that, so I didn't write this, so I am focusing on strings in ADS3, cross S3, cross T4, and I will be studying basically classical string solutions and their semi-classical behavior, and trying to compare to what integrability tells us that these behavior should be. And in particular, we were very much interested in circular strings, because they live in the sector of R cross S3. It's very well known what the semi-classical behavior is. It was calculated for this background. And basically, well, it's R cross S3, so they have the normal shape, which is written here. The charges can be written in terms of the curl, what I call the curly J, which we then take to be very large. The energy is related to the charges by the Virasoro constraints in the usual way. The idea is that, okay, with the circular strings, we want to do a semi-classical calculation, and the semi-classical calculation is very much related to what can be found in ADS5 cross S5. A lot of the calculations so as with any classical strings, we're talking about, from the point of view of integrability, of massive excitations. And in many of the calculations that you can do in the integrability, the massive sector seems to be, how do you say, happy on its own, and doesn't really interact with the massless excitations don't really contribute to, you know, if you're trying to do scattering of massive excitations, the massless excitations are not there. If you do BMN scattering also, you can just focus on the massive sector, and massless excitations, again, do not play a role. But what happens in this case is actually, if you try to do the semi-classical quantization of certain classical strings, what I will try to motivate is the fact that actually the massless excitations do play a role, even though you'd expect them to still decouple. So in terms of the worldsheet semi-classical quantization, you calculate mode, set of modes. They have some fermionic modes, some bosonic modes. And for this particular case, you actually have massless modes as well. There are 4 bosonic massless modes associated to T4 and 4 fermionic massless modes. What happens about these, the frequencies of these modes, is that if once you sum them, basically they cancel out. And what you're left with are the 2 bosonic modes of S3, which are basically 2 of the modes that you'd have from S5. 2 bosonic modes in ADS3, again inherited from ADS5, and 4 fermionic modes. In the same way as the calculation can be done for ADS3, for ADS5 cross S5, you need to, when you sum these modes, you need to regularize by the typical method of Bizert-Zeitlin. You regularize. Actually, you're interested in the non-analytic terms, because we are trying to compare to, we will want to compare to the one loop dressing phase. So these are the terms that you'd compare to that. But so once you do a regularization, you basically obtain exactly what I've written here, which is what I call delta E string. You have it as an expansion in J, in the charge J. And you can hope to compare it actually to now beta ansatz calculation. Why? Because, well, we are talking about a consistent sector which is related to R cross S3, so it's the SU2 sector of the beta ansatz equations. If you do if you analyze this sector, meaning I've written here the beta ansatz equations, of course this dressing phase now is going to be different. Why? Well, so the dressing phase, I've written it as with the coefficient CRS times the charges. Of course, the classical component is just the AFS, because we're talking about strings in R cross S3, so it's we would expect the AFS. This is the massive sector because, well, it's the SU2 massive sector of the theory. And of course, now here the one loop dressing phase is what would come as a semi-classical contribution, and that one will naturally be different from ADS5 cross S5. These coefficients are known. They're known from they're being fixed by crossing symmetry, by scattering of magnons, by BMN scattering. So meaning it's known, they're known and completely defined. This is the relation. And in particular, because we're doing strings in SU2, we're doing circular strings, we know the resolvent that is associated to the one-cut solution in SU2, which is a circular string. I've written here. Of course, if I expand this one-cut solution in the spectral parameter X, I get the classical charges. And how do I now obtain the semi-classics? Well, what I can do is just do the test that Hernandez Lopez did at first place in ADS5 cross S5 when they wanted, in fact, to calculate this one loop perturbation to the dressing phase. So if you indeed do that, what I mean by doing this procedure is just so I have the one cut, again, I have the one cut circular string resolvent. I just take the logarithm of the beta ansatz equations. I convert any sums over the roots into integrals. Sorry. So basically a sum of k of x f of x k plus minus becomes some L integral over the cut dz. So rho is associated to the resolvent by just that. By the usual way. So I basically, take the log of the beta ansatz equations, convert every sum into integrals, and then what I want to do is actually perturb the charges appearing in the dressing phase as I say Qn is just the classical charges plus 1 over square root of lambda delta Qn. And in particular, this actually for the circular string, why the circular string? The circular string is extremely simple, the result that comes from this calculation, because it actually, you can write the solution for the perturbed charges, the perturbed energy in closed form. So it's actually a very simple solution. And basically you solve for delta E, which is it. It's just the delta Q2. And this has a complete closed form in terms of, so it's sum of RS, CRS1, GR plus S, and then QR plus 1, QS minus QS plus 1, QR. So these are all classical charges. So in terms of the classical charges, so it has a closed form expression, and if you expand this expression, of course, what you get is what I've written there as the delta E one loop. So this was the calculation that was done to, in fact, determine in the ADS5 cross S5 to first determine the CRS ones, because they knew what the classical circular string, the semiclassics were, and they could determine the CRS ones. In this case, meaning we already know from other methods what the CRS ones are, and we can actually determine what delta E1 loop is in terms of those CRS1, the one loop perturbation to the dressing phase. And what happens is that, well, if you subtract these two solutions, of course, you get something that is completely non-zero. So we were baffled by this for a long time, and what in fact we found is that the exact reason why these two results don't match is that the massless sector actually plays not the massless sector, but the mixed mass sector. So the interaction between massless particles and massive particles actually plays a role in the perturbative energy correction, semiclassical correction. And where does this contribution come from? From wrapping. So what actually happens, our claim is that it does come from wrapping. And what we did was do we can say somewhat crude calculation, in the sense that it doesn't include or exhaust all contributions to the semiclassical energy, but is definitely of the same order, than of the same order, is actually of the same shape as the result, the mismatch that we find. And it comes from the fact that when you have massless virtual particles winding around circle L, and you calculate, field theory calculation of contributions that can be done from Lucias. Sorry, here I should write Lucias F terms. What happens is that typically these wrapping contributions would be exponentially suppressed, and exponentially suppressed where the exponential is the top of the exponential is kind of proportional to the mass. So if you don't have a mass, and I'm going to go back to whether each one of these contributions actually makes sense on its own, but let's assume that we could just take the massless limit of some of these Lucias F contributions, F-term contributions. So if you actually have a massless particle going around the circle, it will have some contribution that will be leading, that will be of the same order as the perturbative contributions that we're calculating. So if it was massive particles, massive sector, they would just decouple and be exponentially suppressed. But if you have massless virtual particles going around the circle, these are of the same order and will actually contribute to the final result. So with this, this is the mismatch, and where does Lucier F-term calculations? I've presented here some particular solutions, but I'm going to talk a moment about Lucier, and basically the the Lucier F-term calculation originally came for a relativistic theory of particles of mass, I'm going to write S, and with the dispersion relation, so it's relativistic, so the dispersion relation is naturally and you can write this in terms of course, of a rapidity, theta. And you take the volume of the space part, so this was originally in R11, but you then take this to be R. And what you calculate is corrections, so corrections such as this, so you have a particle with momentum p, you have a virtual particle with momentum q. You sum over all possible virtual particles, all possible types of virtual particles. So here it's type B, type A. They might be all of the same type, they might be of different types. Some are fermionic, some are bosonic. And this basically, well, d2q over 2 pi squared, so Green's function, E minus I, this is the momentum, Q1L, and then you have a AABB, so this is the vertex, fourth vertex. But what happens if you take L very large is that you can actually rewrite everything and write the vertex as being on shell. So what happens is that for very large volume, you actually substitute the vertex by an S matrix, and you get the original F term, which is so in terms now, this is in terms of the rapidity. So this is for a, and then you get extra contributions, of course, because I considered one loop, but you can consider higher loops. Some of them will come with double exponentials, double integrals, so you'll have a whole string of contributions. So one thing, of course, this is very hand wave, but if you think that if you're taking S goes to 0, you basically have, what's going to happen is that you can actually have some sort of contribution here from S goes to 0 that is not going to be exponentially suppressed. This is not, meaning it's not that all the integral is not going to be exponentially suppressed, because in fact what shows up in the integral is minus IQL, where you define Q in terms of, so, sorry, Q, no, it's Q star, where do you define, sorry, just 1 second. Minus IQL, so Q is Q of Q star. Sorry, so Q star is going to be the momentum. This is going to be the energy. And what happens is that typically you have something like this, where the minimum of that exponential is going to be in the mass S. But if you have S goes to 0, basically the minimum goes to really 0, and at this exact point, the contribution will be non-exponentially suppressed. But this is for relativistic theories. So for our case, some calculations have been done. So the first calculation that I'm going to mention is that so Heller, Janicke, and Bukowski actually calculated the F-term contribution from sum of fluctuations. So they actually assume fluctuations above some string background. The string background that they chose is just a single excitation, a magnon excitation. And they assume that they had a virtual particle winding around the cylinder m times. So they actually not only once, but m times. And you can see that the exponential comes with the m times. So the leading one would be basically m equals 1, and then the other ones are even subleading. All of them are exponentially suppressed, at least with mass equals 0. And the leading one is m equals 1. The other ones would be more exponentially suppressed. Also, from a TBA point of view, so Beinok and Janek actually calculated. You'll have a you have basically a leading contribution, yes. So you would have to actually sum every single contribution that you could think of any particles going. The leading, well, all of them are of the same order. All of them are of the same order, exactly. So this is why I'm saying that our calculation does not give the full result as much as it shows that, at least up to the order that we calculated, that it definitely contributes to the exact same order that mismatch appears. So again, from the TBA, so Beinok and Janek actually, what they've done is assume the multi-particle state of particles of type A, and assume now one virtual particle winding around the circle L only once. And they calculated, they expanded the TBA basically, and they calculated, so there's a, well, maybe I'm not, so basically in the TBA you have that, first of all you have that the energy of some Ni particles, depending on L, is equal to m where the epsilon of theta prime, so the theta i's are defined, quantities of the solutions are defined by the poles of the integral. And you have also that epsilon of theta is equal to m L cos of theta plus sum of the log of the S matrix of theta minus theta j. So this is for relativistic theories. So this is the kernel, which is the log, the derivative of the log of the S matrix. And this is a nonlinear integral equation that defines epsilon iteratively. Of course, if you have a mass scale. So if you have a mass scale, m, you can actually see that you can keep on solving the epsilon of theta kind of order by order, and you basically, the next order will be exponentially suppressed. This is not quite true, of course, if you have massless. Actually, if you do the related TBA for massless case, you can, meaning this mass scale gets reabsorbed, disappears, and you do not have a mass scale. What you have to do is actually to solve these equations and see if the solution that you get for the epsilon converges at some point to a particular value, or if by any chance, meaning you could just have it in such a way that you couldn't find a solution, because every time you try to iterate in some way, you don't get any convergence. But but when you don't have a mass, especially massless TBA, basically you cannot use the, well, you cannot anymore use the mass scale to actually do the iteration. No. You can actually define a massless TBA, and you can show. I thought that. So. It could not be exactly. Exactly. So for the massless TBA, what happens is that this one will include every single one of these wrapping corrections, of course, and you can't separate them. Yeah. So, and for the massless massive TBA, if such a thing can be found, it's the same problem. So this is the TBA, and what they found is that by using the same methods, they could find a multi-particle state on the outside of physical particles and one virtual particle going around once. What happens in our case is actually, so circular string. The circular string is a multi-particle state. But as I mentioned, for sure, if we did just one winding, why would I choose one winding instead of 2 or 3 or n? Because they're all of the same order. So what we try to actually do, the calculation that we try to do, well, first we did one winding and we saw, we obtained results that are of the order that we want, but the coefficients are definitely incorrect. What we did was like a kind of adjustment between this formula and this formula, which is what is written there, which is a kind of multi-particle physical state and sum over n windings. In such a way, because again, all the windings are of the same order, so we don't have any gauge of choosing small winding or large winding. And by using the mixed mass sector, so the S now that is written there is basically the S matrix between a massless virtual particle and a massive excitation out of these K excitations. And you can actually do the calculation. And what you find is, sorry, I just want to not only we find the right order of the results, but we also find, in fact, the same general shape of the expansion, apart from a factor of 2. Again, coincidental, not. So our guess is that if you actually manage to really do the full TBA for that includes the massless massive sector, that somehow any other contributions other than just winding of particles of massless particles m times need to somehow cancel, because the shape is the same. So it's or they all contribute to cancel the factor of 2. This is not completely obvious, but it's not. But definitely, there's some, meaning these contributions, just these contributions seem to already be of the correct shape. So I would like to finish with a set of many. We've tried, of course, many different checks and tweaks to what we were calculating to see first if we could determine the factor of 2 apart from actually determining the full TBA. So one of the things is that, for example, in terms of mismatches, circular strings in SU2 are not the only ones that have a mismatch. So we have the SU2 circular strings and we have the SL2 circular strings. So here we have that the K is basically a L over 2 J charge, so in S3. The SL2 K is S charge, so ADS also L over 2. And in this case, if we do the same calculation, again, we get the correct order, but we do not get the correct coefficients. So it's not, meaning it's just a factor of 2 times the mismatch or anything of the type. Huh? No, in this case, even even each term doesn't match, the coefficients don't match. So we get the correct 1 over j cubed, 1 over j fifth. So it's the correct orders, but the coefficients actually are not the same. So we get k minus m to the cube time, meaning because here for the SL2 you have both k and in the winding m for the resolvent, and the coefficients definitely do not match. So also we need to make sure that we don't break the agreement that you can find for the SL2 short strings and also for the giant magnon. So it seems that meaning if you have very large multiparticle states that there's a mismatch, but if you don't have such a large state, there is agreement, and definitely meaning this needs to be taken into account. Somehow the massless particles do not cancel out their contribution. And of course there's all of the other terms that if you did the massless TBA and meaning if you had a massless massive TBA and you could actually, instead of doing an expansion of this log, actually do the whole calculation with the log, you would get all the massless contributions. And in that case, the hope would be that you could actually determine the full difference between the string semiclassical calculation and the beta ansatz massive sector calculation. So that's basically it. So this formula is definitely a trial formula, even not meaning it's just a kind of trying to do a multiparticle state with an n winding. Of course, with the winding, meaning if you can see here, we didn't assume massless scattering, so that we would get kind of a -1 to the n if we did n winding and we considered the -1 to the n. In fact, for the calculation of the circular strings, it doesn't contribute because the odd terms actually are 0 in the calculation, so it doesn't make a difference. But once again, that formula is just, how do you say, prototype of what multiparticle physical state with m winding would be. And we would have, well, again, for the massless sector, probably we wouldn't even have full Lucias contributions because they don't separate. So these are all the open questions, trying to understand everything. Unfortunately, for most things at the moment, more things don't work than they do. So we're still stuck with how to deal with the massive massless sector and how the massless particles actually contribute to the semiclassics of strings in this background. Thank you. Sorry? But this is what that's what Arkady did, meaning they calculated these coefficients CRS, which were yeah. No, the CRSs that they found were not the same as what you found. It's exactly the order of this mismatch. No, meaning you do the calculation with one, you do the calculation with the other, and this is what you obtain. The difference is exactly this. So sure, they're almost the same, but the factors of 1/2 make a big difference in these cases. For the SL2 case, if you do the calculation, you would get the same difference, yes. But yes, that's exactly how they tried to calculate. But then you came, meaning there was the calculations from the crossing, from the magnons of Michael, from the BMN scattering. So indeed.